Hello everybody, Dr. Powers here. We're going to be looking at a couple new features in statpowers. What they are some non-parametric tests that have been added, and we're going to look at a few of them, starting with one sample analysis. So, sorry, I should say one variable analysis. So what I have here is a kind of some simulated data where we have control group, a treatment, and two different treatment groups, and it's actually a relatively small sample size. If I wanted to just look at in fact, I'm gonna simulate an even smaller sample size of, let's say, 15. Okay, I'm gonna sample that, and I'm interested in the measurement, the before measurement, like what these numbers in the before. Now, I'm not giving you any context. This is very abstract, so it's just some number. I'm looking at this distribution. So let's analyze. I'm going to just look at before numbers, and what we can see here, if we look at, let's just look at a chart of let's look at a histogram. We have this data, and if we conclude that this is not close enough to the normal distribution for me to use a t-test, the question is, what do you do? Well, we're going to use a non-parametric test, and instead of trying to decide something about the mean of the population, we're going to make some sort of determination about the median. There's a couple different tests for the median that I've implemented, and let's say we're interested in testing whether or not there's evidence that the median for the population is equal to 20. All right, I'm going to test that by going under test for the median, I'm going to put in 20 for the null median value. I'm using theta for median here. So we have three different tests: the Pitman test, the sign test, and the Wilcoxon rank sum test. So they each are testing in a different way. Very briefly, the Pitman test as a non-parametric test, the assumption here is that the null assumption, the null hypothesis, is that the median of the population is 20 here, right? And so under the null hypothesis, every observation is equally likely to have been above or below the median. Right? That's the idea of a median. So what we look at is, for each value that we've observed, we look at the difference between what we've observed and that hypothesized median of 20. That difference, let's say we have observed a 22.7, right? That's 2.7 more than 20. Under the null hypothesis, it's equally likely to have observed a difference of 2.7 as it is a difference of negative 2.7, because that's the idea of a median. So what we do is we calculate the sum of the positive differences, and we look at all of the, if we were to look at all the different possible permutations of changing the signs of these differences that have observed, we look at of all the different permutations there are, and there's of course a lot of them. It's 2 to the power of the sample size, which gets pretty big. We count how many of those permutations result in a sum that is greater than or equal to what we actually observed. That's the p-value. Okay, so the p-value we got here is 0.02877. So it's actually what we observed would be pretty unlikely if the median is actually 20. The sign test looks at it from a different perspective. It doesn't look at the magnitude of the magnitude of difference. It just looks at whether an observation is greater than 20 or less than 20. And from this we look at it's just a binomial. Every observation under the null hypothesis is equally likely to have been above or below the median, and so you kind of look at, okay, well, in this case 10 of these observations were above 20. If in a binomial, if you flip a coin, flip a coin, what did we have in the sample size? 15 times. The chances that you get 10 or more heads, right? Or anyway, more extreme than 10. And it's a two-tailed test, so it's doubled. That's going to be our p-value here. which is actually not as significant. Of course, it's a simpler test because it doesn't take into account the magnitude of difference from the median. So the sign test is not as powerful of a test, but it's easier to do. The Wilcoxon rank sum test, it's more powerful than the sign test, and the idea for the Wilcoxon rank sum test is the difference between what is observed and the median is, we look at that difference and then we rank those from lowest to highest, and we are summing up the ranks. We have the positive ranks and the negative ranks, and then we look at the in this case I think we're looking at the greater of the two, the W plus, which is the sum of the positive ranks. Anyway, it has its own distribution. I don't want to get too bogged down in the details because I'm just showing you what statpowers does. So you get p-values for Pitman test, sign test, and rank Wilcoxon rank sum test. This is for when you have one variable and one sample. What I want to look at next is I'm going to compare before and after as a paired test, or paired differences. So I'm going to analyze before and after, and what I'm interested in looking at the differences of it's like after minus before. So so you can see like before, after, this is a difference of negative 0.94. Okay, so that's the analysis I'm going to be doing. Let's take a look at test for the median. This is the median difference. The median difference is, let's do a median difference 0. Well, the sign test and the Wilcoxon rank sum test, they're the exact same for differences, just because when you do a paired t-test, you're just looking at it's just a one sample test, really. You just calculate differences and you do a t-test on one sample. Well, the same thing applies here. Okay, so you can get those for the median of differences. You also have, let's see, I think we have correlation. This will calculate a couple of correlations that are non-parametric correlations. Spearman's correlation coefficient is calculated, and a hypothesis test of whether there's a significant correlation. So if, for example, our data was ordinal instead of like interval, right, it wouldn't be appropriate to look at the Pearson correlation, but you can look at the rank correlation, and that's the Spearman correlation. And then Kendall's tau is more complicated, and it's arguably it's a better representation of the non-parametric correlation. But anyway, you can see the tests are done on whether or not these parameters are equal to 0 or not. So they're just two-tailed tests for correlation, for non-parametric correlation. All right, now let's look at. Let's just say we want to look at just the treatment, the difference between the control and treatment 1. So I'm actually going to modify this to, let's do 10 from control and 10 from treatment 1. And I'm going to resample. And I'm going to look at the after based on group. So, after group by group, I'm going to analyze that. So I just want to show you, if you have two independent sample, we have the control group and we have treatment 1, the non-parametric test that has been added to look at this is found down. Actually, we have a couple of them. We have a test for the equality of means, medians, and then this is just looking. The Mann-Whitney test is again, it's a non-parametric test for two independent samples. So the samples could have had different sizes, right? The null hypothesis is that the two population medians are the same. The alternative is that the population medians are different, and you get the U statistic and a p-value. The Mann-Whitney test is also generalized to, it's generalized, the Kruskal-Wallis test generalizes it to a larger sample size. But anyway, it's given, and then the Moods median test is it uses an approximation of a chi-square distribution, and you can see it's Moods median test is looking at whether the proportion that are greater than the median for the two groups is significantly different. So the Moods median test is basically like a two proportion test. It's kind of like a well, it is a two proportion test. I mean, in this case, if you're looking, so the group median is found, and we look at and see like what proportion is greater than the group median in the first group versus the second group, and we want to see if those two proportions are significantly different. So this is just a two proportion test essentially, and thus a chi-square statistic is used. The Kolmogorov-Smirnov test, which I pronounce poorly, pardon my Russian, is looking at a similar thing. This test is looking at the empirical CDFs of the two groups and seeing if how significantly different they are. So let's just take a quick look at that. So here, the idea is if you were to take the red for the control and continue that red line across at the bottom and the top, we look at the maximum difference between the two CDF curves, the cumulative distribution function curves. And the maximum, if the two populations are very different, then we would see a very big difference in their CDFs, which we do here. We see probably the largest difference is happening right around 16 point something, and that's a difference of 0.45 or something like that. 0.4 is the largest difference. And that's a very significant difference when you're comparing two sample distributions of this size. You can see the p-value is 0.0028. This is the approximate p-value. It also gives I'm not sure what that other thing is looking at. I'll have to just check on that that other value here. Okay, so let's add another stratum. Let's add treatment 2 and put 10 sample size in there. Let's sample and let's look at analyzing after by group again. Now we're going to have three samples. We have treatment 1, treatment 2, and the control. Okay. And let's just take a quick look at the ridgeline plot. You can see we have they look like they're quite different from each other. This is very smoothed out though. Let's lower the bandwidth to see a little bit more of the distribution shape. So there's a lot more. These are very small sample sizes to be estimating the density functions from, but you can definitely see treatment 1 has a lot more lower values than in treatment 2 or the control. So anyhow, let's take a look down at what tests we can do. The test for different medians is the non-parametric test. And the null is that all population medians are equal. The null hypothesis, or the alternative, is that at least one of the medians differs. Very similar to the ANOVA test for the difference of means, right? If the test finds a significant difference, it doesn't tell you which of the groups has a significantly different median. It just says one of them is. And so the Kruskal-Wallis test is the non-parametric test for median that's been implemented, and it basically is just you got the t statistic, or this. It's not a t distribution. It's called t, and the approximate p-value. So this is approximated based on an asymptotic distribution for the test statistic distribution. And Moods median test is also done, and this is, again, it's just essentially a independence test. We want to see if the the proportion that are greater than the null median is significantly different across groups. And you can see they have similar p-values, and because they're testing slightly different things, but you will often get similar results. Let's increase our sample sizes and see if we have more. Now I'm going to just sample again and do the same grouped analysis. Okay, so I have a larger sample size now. I'm just kind of curious to look. Let's look at the empirical CDFs, just see how different they look. Okay, you can see that the treatment 1 is actually pretty similar, or treatment 2 is similar to the control, but treatment 1 seems like it's lower, right? And you can see that the medians of the three distributions can be found when you look at where it is 0.5 cross. That's the sample medians, at least, right? And actually, it looks like the sample median for treatment 2 and the control are the same. All right, let's go down to the test for medians. So the Kruskal-Wallis test finds a p-value of 0.001, but the Moods median test finds a much higher p-value. So I think Moods median test is because it's not interested in testing like how much of a difference there is from the median. It's just looking at whether or not an observation is above or below. It's not going to be quite as powerful of a test. But anyway, I don't want to get too deep into what's more powerful or not. I just want to highlight these features in statpowers, showing you where you can get the results for tests for the median, which are the non-parametric tests that have been added. And then, of course, remember I also put in that the Spearman and like the non-parametric correlation. So that's it. Short update. Hope you found this interesting. Just trying to make this better and better. So enjoy your analysis. Bye.